Morning everyone. So we're going to finish off our review in looking at our spectroscopic techniques. This one here was basically us going on as experimenters and investigators, trying to collect as much information from different angles using mass spectrometry, using NMR, using IR radiation to try to get a sense of what the chemical that we created is, what's the amount of that chemical in the solution, and also trying to figure out the identity of the compound. So spectroscopic techniques. I didn't have any other summary notes, so let's just walk our way through our notes package again. Let's just do some highlights here. So spectroscopic techniques, first thing is in your data booklet, you're actually given quite a lot of information. You're given the IR, the wave numbers that the bonds are sensitive in section 26, the NMR, so it's protons that are flipping. In that case there, we measure it from TMS, how far it's sort of shifted from that position, as well as MS fragments for mass spectra. When we go and bombard and break up fragments, what are the pieces that are left over? As I mentioned here, spectroscopic techniques are used for different purposes. We can do qualitative analysis. We can just figure out, is there the presence of something, for example, a forbidden species in an athlete's blood? So it's just, is it there or is it not there? More so, we don't just stop at qualitative, we want to switch it over to quantitative, which is, if it's there, I want you to actually measure the amount. How much is actually present? So when you're driving, you may be able to have a allowable limit. If it's over that limit, then it becomes a trouble, but we can measure how much alcohol is inside the breath. Or even structural analysis here, again, especially when you do organic chemistry, although theoretically we can predict mechanisms, we can predict this is what's supposed to be what we've gotten as a product, we can actually use structural analysis, use these techniques, IR, NMR, to try to figure out the purity of the product that we got and how good a procedure was. So a couple tools that we use in this section. First one was a general one called degree of unsaturation, or index of hydrogen deficiency, IHD. Basically what we said here is, we said every time you have 1 degree of unsaturation, you've either formed a multiple bond, you've either gone from a single bond to a double bond, triple bond, a multiple bond here, or every time you form a ring, for each ring, we'd end up losing two hydrogens. That definitely unsaturates your compound. It takes us from alkanes to alkenes and cyclic compounds there. But knowing how many H's there are could give me some information with what functionality that we have later on. It does come with a formula here. I wouldn't bother memorizing this because it's easy enough. Just if you're given a formula here, let's do C double bond. Let's do something like that. If I want to ask you how many degrees of unsaturation, I see that a single bond has become a double bond. So basically I would have lost, so that's 1 degree there. A single bond has become a double bond. I lost 1 degree, and I lost another degree for the triple bond. So this one here already has 3 degrees of unsaturation. If you go from the alkane, which is CN 2n plus 2, so C4H10, I would expect you have 3 degrees of unsaturation, so I would have lost 6 hydrogens. I would expect C4H6. You can verify that for yourself here. 2 hydrogens here, 1 and 1 there. So C4, oh sorry, I can't add, so C4H4, so minus 6 hydrogen. Every time you lose a degree of saturation, you lose 2 hydrogens. So a double bond, triple bond, a ring, an aromatic like benzene, which would have cyclic and 3, so that's 4, so we've lost a total of 8 hydrogens there. So you can practice through with either the formula with these compounds. A lot of these compounds here are a lot more complicated with rings actually fused together, but you can still either use the formula to try to figure out how many degrees of unsaturation. This next part here is sort of preface before we look into the MS and IR in more detail. It turns out we can do in general spectroscopy, and basically what it's doing is we're using different wavelengths of radiation and we're analyzing how matter will interact with it. So this is just a really broad stroke. I know our EM spectrum is actually visible, is actually a very tiny region. We can utilize the IR this time. We can use UV radiation. What do each radiation tell us about the compound itself? Again, we're going to be introducing these methods upcoming here. So just from, I think I started off here with low energy, and it's going to get higher onto the backside here. Radio waves are typically used for like thermal imaging. In this case here, radio waves was used eventually for NMR, so proton slipping. So radio waves for NMR. Even though we needed an external magnetic field, we just sort of overlay it with the scanning through radio frequencies when the proton ends up flipping. So we'll do that in more detail. Microwaves, turns out it gives us information about our IR radiation. That's sort of this overlap between micro and infrared. Basically bonds that have changes in dipole moment. That's a really important feature here. A change in dipole moment is a thing that actually is sensitive to IR radiation. It doesn't mean I have to be polar overall. We did the example of carbon dioxide. Overall, the polarity of the C and double bond O, it actually cancels out. We're actually nonpolar. But depending on how this ends up stretching on itself, maybe it's asymmetric, maybe it's elongated on one side and short on the other side, because there is a temporary dipole that's set up, you can use this infrared radiation to actually get this to stretch, bend, and absorb that radiation a little bit more. In our atmosphere, this causes a problem with greenhouse effect, but in this case here, we're purposely tossing in IR, or infrared radiation. I always want to say infrared, but infrared to absorb. We didn't do much with the visible and UV because we did that more in grade 11. This one is using light as a electron exciting source here. Basically, this is on the order, remember we did like Lyman series, Balmer series, things like that, especially for hydrogen. 2 to 1 was already big enough to be in the UV region. Maybe this is an emission spectra where the electron fell from 2 to 1 and then releasing off a UV photon. Or maybe we're shining in a UV light. Nobody has the time to actually send in exactly that exact UV radiation. So if you remember from chapter 3, we decide to send in the entire Roy G. Biv. Red, orange, don't have all the colors here. Roy G. Biv. We send in all the colors, and whichever ones happen to correspond with exact energy transitions, they would just take away that exact color. Eventually, when those electrons end up falling, we would just see the band, maybe the red, the green. Remember, for the emission spectra, it actually does get closer together on the high energy side, the 400 nanometer side. So this one here is more an emission spectra, and the other one is more an absorption spectra. We did that more so in chapter 3, chapter 2 last year. X-rays here, we touched on that a little bit in the section. Basically, you just need to know crystallography is used to help me find the bond distance and the bond angle. There's some notable cases like DNA structure was found in this manner. We saw that the shadow formed from the double helix structure. We're just basically trying to get as much information as we can. So without further ado, let's just have an overview look. We're going to start off with mass spectrometry here. There's different types of mass spectrometers. We can have gas spectrometers, liquid chromatographers, things like that. But mass spectrometers in general, I pulled the diagram from chapter 2 again here. Although they say in the new curriculum you don't need to know all the steps again, I'm just going to quickly overview it with you. You start off by atomizing the sample. You first make it a gas state. The second part is important here, which is I'm going to purposely send in fast-moving electrons, and I'm hoping to engineer some crashes so that when the electron hits the compound, I'm hoping the compound will end up dislodging its own electron. I'm trying to make the compound here charged so that later on I can do step 3. I can punch it through an electric field. I can give it some, now that everything is a positive charge having lost an electron, I can put the negative plate and positive plate here. I can give it some directionality to it. It's going to be sent through the device. I'm going to quickly scan through a bunch of magnetic field settings. If the magnetic field is too weak, basically everything hits on the far side and never hits the detector. As I slowly ramp up the magnetic field, it slowly pulls those lighter ones down the rest of the tunnel. As I slowly increase the magnetic field even further, those lighter ones end up not making it anymore. The heavier ones here, which used to not make it, is now able to make it. And all I do at the end, I might need to amplify the signal, is I count how many hits are there based on each setting. When I do that there, I end up with what's called the mass spectrum. This is sort of like no deflection and it steadily gets stronger. It is plotted against what's called the M per Z, so it's a mass per charge ratio. If I engineered the car crashes properly, I'm hoping that I got M. I managed to knock off 1 electron, so the charge is actually just +1. If I go mass divided by +1, essentially this is just the mass. This is also how we find relative abundances in chapter 2 as well. Every now and then, maybe the electrons actually dislodge 2. Maybe it's going to actually end up being M+. Now I'm actually M2+, having lost another electron. Because, unfortunately, the deflection is a mass per charge, that might actually conflict with things. Maybe I do actually have this molar mass, but once I divide by 2, I'm not going to hit at the same setting as I should have hit. So that becomes a problem. We try to keep this chamber under a really high vacuum to try to prevent any unnecessary collisions so that the ones that are supposed to hit at that setting are actually able to make it through the end. It's a little bit hard, they say in the textbook, to analyze every single peak because not only is this electron going to be bounced off, especially because they're so high energy electrons, sometimes a big fragment like this ends up dislodging into smaller fragments. When that happens, one side gets the positive, the other side doesn't. It's only the charged particle that's sent through the device, so it's only the charged particle that gets detected on this mass spectrum. So what we're going to do here on a mass spectrum, a couple important notes. We're going to treat the heaviest one here as the parent peak. We usually call it the molecular ion peak. This is best case scenario. I imagine I have my molecule, I sent in my fast moving electrons, and I managed to do exactly what I wanted. I kicked off one electron, but I made sure that this entire thing stayed intact. So the molar mass is still 46. I can do a little bit of empirical formula, molecular formula work with that, because that one there is my true molar mass. And then depending on the actual fragmentation pattern, depending on what I'm actually breaking off, there's two ways of looking at it. I get these bars here. Either look at the bar itself. Oh, this bar here is 15. On your data booklet, 15 is actually coincidental the mass of a CH3 grouping. So I look at this one here. Oh, if I manage to chop off this left-hand side, this side is positive. That's what's explaining my 15 peak here. The height of the peak tells me how much of that methyl peak did we get. So you can look at the peak number by itself, or you can look for the difference. You can look for, was a molar mass of 46. The difference between 46 and 31 is also 15. I can look up 15 in that fashion, or I can look for the remnant. If when this collision happened, it wasn't the left-hand guy that got positive, what happens if it was the right-hand guy that got positive? In that case there, I get my 31 peak. My 31 peak is what's left over, having lost that methyl peak. So in this case here, you can look at the bar itself, or you can look at the difference and look at the remnant that's left over. Again, what's important here is for you to note it's only the charged fragment that gets detected. So if it's not charged, it won't get sent through the detector at all. It won't be counted at the end. So make sure you mention that part there. Realistically, because we're doing a quick scan of this, it's not exactly going to be like no signal, and suddenly just a vertical signal like that. Essentially, it's actually going to sort of be a sort of area under a curve like that. It's actually the area, the integration trace under this one here. We don't really get the integration trace for this right here, but it's the area under the peak that actually shows you the relative abundance. If I spend the same amount of time at each given setting, I know the relative distribution of the fragments. Again, we did that for isotopes for the different versions. So in a nutshell, that one there was mass spectroscopy. The third technique that we used here was IR spectroscopy here. IR radiation, infrared radiation, it doesn't have enough energy for electron transitions. It doesn't actually jump electrons from shell to shell, but we're going to start thinking of bonds as little springs themselves. Springs naturally will vibrate already. They're constantly stretching, contracting, especially the diatomics are a little less exciting because I can just stretch and contract. But if I have something like water, I can actually do some sort of bringing my arms together or apart. I can change the bond lengths. A lot more variations in terms of what types of stretches, what types of frequencies I would naturally be vibrating at. We can have a generalization here. If I'm a lighter atom, so let's say a diatomic and it was HF as opposed to HI or so, lighter atoms typically have higher frequencies. They're going to show up at higher wave numbers. Or multiple bonds here, they're a little bit more rigid, they're a little bit more tightly wound springs, and because of the tightness, that's also generally going to give you high frequencies. We did our data booklet in terms of a guy called wave number. This is similar to just frequency. Frequency in general, we just used hertz. We're going to, frequency is proportional to energy, so that's why we use frequency there. Frequency, if you use the universal wave equation, C is equal to F lambda here. Frequency is actually C over lambda. It's a reciprocal wavelength. This one here actually rescales it through the speed of light. It is that reciprocal wavelength here. Wavelength in general would have been in nanometers. I would have been a nanometer minus 1. But in this case here, we actually rescale it here so that I convert, let's say 10 to the 7 nanometers is actually 1 centimeter. So therefore, I have that same frequency. I'm going to at that point call it a wave number. And it's actually going to quote it as a centimeter minus 1. That allows my wave numbers to be in the thousands, so it's easier to track versus carrying around really big powers. So we looked at a few examples here. So we talked about the strength of the string itself. So a stronger spring here, it's a higher wave number that's needed to actually stretch it. When I have a polyatomic species, I have many more modes, many more ways of actually doing the stretching and contracting here. And you see, depending on which mode it is, that corresponds a different wave number. So all we're going to do is we're going to send in a whole bunch of IR radiations. If I happen to have springs that are naturally already stretching at these frequencies, if the wave number is exactly the right IR radiation, I can actually absorb that frequency, and I can just do that a little more dramatically. I'm going to send in all my wavelengths. Remember, we're going to start off for these IR plots, we're going to start off with 100% transmittance. This is assuming that there's no bonds absorbing anything, and depending if I do actually have that particular bond, when I send in that exact wave number, it actually is going to absorb some of it. My transmission is actually going to decrease. The wave number here is specific to what type of stretching, what type of bond that we're doing. And the intensity of the peak here is shown by how much absorption there is. That would be indicative a little bit of how much of that bond is present. Remember, IR radiation, sure, it's good to tell maybe what bonds are present, but it's much more useful to actually tell what bonds are not present. So for example, we saw the OH is supposed to have a broadening absorption. We're supposed to get this sort of widening of the peak. If I'm not seeing that widening here, I can actually say probably no OH in this first molecule here. And depending on which bond, unfortunately this one looks at individual bonds, just knowing it has, for example, a C to H bond, I don't know whether it's an alkane, C-double-bond-O, I don't know if it's aldehyde or ketone, I still have some freedom in sort of which functional group it is, but at least it gives me some information with which bonds are definitely not there, so which functional groups are definitely not there. Be careful when you look at the axes here. Sometimes it is linearly scaled, so every step is the same. But you'll notice here, going from here to here is only 400 nanometers, whereas going from roughly the same size, this is now 1,000 nanometers. Sometimes there it's actually not linear. So just watch out for that when you're actually matching up the wave number. We typically have been doing the analysis up here. So those are trying to identify, again, it's much better to identify the absence of bonds. So if I don't see a peak, I know definitely it's not there, whereas if I do see a peak, it's sort of preliminary evidence it might be there. If you did this in more detail here, you actually have what's called the fingerprint region between 300 and 1400. You notice that still is a very wide range, but technically we get, if you actually look at those peaks, again, you're not going to be analyzing every single peak that's present, but if you can look at that fingerprint region here, the reason why they call it a fingerprint is that part there is a lot more informative with what bonds are actually present. So use your data booklet with the IR spectra and try to identify which bonds are present. Again, don't forget, it also identifies which is not present. So if you don't have a particular peak here, it can also give you that information. So that one was method number 3. Method number 4 here, we're going to look at NMR. It turns out chemicals that have odd number protons, we specifically zoomed in on proton NMR. You could hypothetically do carbon NMR, phosphorus NMR, and whatnot. The emphasis here, again, just specifying here, it's protons that are flipping. Okay, so protons themselves, protons are the ones that are in the nuclei. Protons, like electrons, have this notion called spin. They're either going to be spin up or spin down, just like electrons have spin. So all we're going to do here is the spin frequency. First thing we're going to do is we're going to put it in an external field. So let's say I have a north pole and a south pole. So it's an external B field, external magnetic field. And essentially by putting on that external field here, we do the lines how a test north pole would go. Basically what would happen is all my protons would align either with the magnetic field or they're going to align against the magnetic field. If they're with the magnetic field at this point here, they're going to be the lower energy. If they're against, they're perfectly anti-parallel, they're going to be higher energy. This energy gap here corresponds nicely inside that radio region. So what's going to happen here is once I put on the external field, I'm going to have some of them that's in this low proton spin configuration. I'm going to scan through my radio frequencies, and when the radio frequency is exactly the gap that we need, the proton can flip from the stable configuration to the unstable configuration. So in this picture here, let's say downspin to the upspin. So we're doing two things here. We're using the magnetic field here to force the protons into one configuration or the other, parallel or anti-parallel. And then we're scanning radio frequencies. We're superimposing that there. And as we scan over the radio frequencies, once the radio frequency is exactly the right energy reading, the protons flip and we actually sense that signal there. That signal here is it's not an absolute, so we have to create TMS as our reference, but depending on how far away from TMS we are, we can identify which functional groups are present. This was really useful in defining like hydrogen environments and actually distinguishing how the hydrogens are actually attached in your molecule. So that I already gone over with you here. Nice picture for it. This one here is our TMS, tetramethylsilane. They do like asking you the question, why is this our standard? So a couple things here. We use silicon as our central here. Silicon has a different range than carbon. So most of our organic molecules actually deal with carbon compounds. I don't want my TMS signal, or what would be called the zero signal, I don't want that conflicting with where my real peaks would be for my compound. So I choose silicon, a little bit less electronegative, so it's going to be totally different, and that way I can measure my compound with carbons different from this part. We're looking at hydrogen environments because hydrogen environments can either be upspins or downspins, totally independent of each other. In this case here, we have all 12 protons, so we have 12. The number of hydrogens is actually given by the area under the peak. So this is actually going to give us a really notable signal, really easy to identify. In fact, Mrs. Rabari says, usually when you scan through radio frequencies, it actually goes in cycles. It scans like low to high, low to high, low to high, low to high. And basically, upon running it multiple times, you're going to at first get some background noise, but upon more cycles of it here, you're going to gradually get this getting higher and higher and higher and higher by ratio. And basically, the ratio will tell you how many are in that exact environment. In this case here, because we have 12, we're going to get already a very high peak for having 12 H's. Sometimes it is really hard to see just based on the height of the peak. That's when they actually do the integrated trace. They draw a line just going left to right. You just look at the gap. Well, that gap there is a distance of 1. This gap here is 3 times bigger. Maybe the peak here, maybe not necessarily 3 times big, but at least area-wise here, it's 3 times as big by ratio. So we have 3 more in that environment, 3 in this environment, and only 1 in this environment here. So back to TMS here, it's also chemically inert, so it doesn't really react with the substances that we do. It's soluble in a lot of things. Easily removed is another good feature. So you put it in, you do your NMR study, and you can just very easily evaporate it, right? You just need it slightly hotter than room temperature here, and basically it's gone again. No interference, and yeah. So that's why we use TMS as a reference, and then basically our shifts. Our shift would depend on the actual external magnetic field, but hopefully I can measure the shift away from TMS because both the TMS and my actual chemicals are in the same field. I can still measure how different, how far away, how far downfield. Okay, downfield is a bigger shift. How far downfield are my signals. Chemical shift here, they do a little bit more detail. They do measure it based on TMS, so they give you a number for that there. If you compare it to your data booklet, we actually find that data booklet actually gives us a huge range. It's not super easy, but if you can match it up, this one here is the best because it actually identifies not just, oh, I might have this bond, it actually has this bond in this environment where the hydrogens on my neighbors are in a certain fashion. This part here, we started off with a low-res signal. A low-res signal, we're not going to get any splitting. So basically, if I zoomed in on this peak here, I would get sort of one peak, maybe another peak like this. When we went to the high-res signal, we do exactly the same thing, but the high-res signal is affected by neighboring hydrogens split peaks. So what will end up happening here is your low-res signal may have only given you sort of a broad stroke, big diagram of where the peaks actually occurred, but in case I have other hydrogens, we're going to move into this on the next slide as well, but for example here, I have 3 hydrogens, so I would imagine this is my taller peak. This one here is my CHO group, the H for that group. Again, I'm just focusing on the hydrogen part. It's the proton that's flipping that's giving me the signal. But what's going to happen here is, for example, for this methyl group, because this hydrogen here can also be upspin or downspin, it can either help the external field or harm the magnetic field. When it helps it, it causes the splitting here to be one way. When it goes against, it's going to split my peak into 2. So this one here, which all in the low-res case look like one gigantic peak, actually is split up into 2 shallower peaks. So one is less stable, and one is more stable. We're going to get into sort of Pascal's triangle on the next side as well. We have a sort of 1-to-1 ratio. We just get a little more, exactly that word, resolution, a little bit more detail from that peak there. So we would call that here a 3-hydrogen doublet. 3 hydrogen because we have 3 hydrogens in that environment, and all of them are being split into 2 signals because our neighbor has 1 hydrogen. In fact, we're going to always split into the number of neighboring hydrogens plus 1. So with that, let's say this hydrogen, the CHO group, it was at a different shifting, so it was a little bit farther away. If the H is over here, all of these can be either upspin or downspin. If you do all your configurations up, 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 down, down, up, up, down, and whatnot, because I have 3 neighbors, I would expect a splitting to be split into 4. And if you look at Pascal's triangle, 1, 1, 1, 1, 2, 1, the 4 splitting case is 1, 3, 3, 1. I would expect this one here to be a quartet. So again, we're getting a little more resolution because of how many hydrogen neighbors, because they could be either aligned with, helping the field, or harming the field here. They can be independent. The ratios and how many I split into here, this one here is 1 hydrogen quartet. They will only go up to a quartet. So in case I have, let's say I have somehow I have another methyl group on this side here, I would actually need to split into 7. Pascal's triangle would still give me how many, but in that case there, I would just call it a complex splitting pattern, more than 4. And it's just going to look like just a big mess on your diagram. When they do questions and they just give you a quick blob, let's see if I have one here. When they just give you a quick blob, they're not expecting you to actually count how many peaks. That's what they're just trying to say. Oh, these are just complex. Meaning they're going to have many hydrogen neighbors and they're splitting into many, many peaks. So let's see if I missed anything here. Even when you compare to the data booklet here, your data booklet might give you a large range splitting from TMS, okay, how far away it is from TMS here. The actual still might be a little bit different, but hopefully you can recognize, again, if I have a particular, between 9 and 13, my real one was 11, maybe I have a hydrogen in a carboxyl environment or an aldehyde environment. The next page over talks about the splitting that we talked about. Essentially, we are still interested in the hydrogens on the CH3, but because the hydrogen on my nearest neighbor, it could be upspin or downspin, it can end up giving me a little more resolution. It can split my low resolution peak into a higher detailed splitting pattern there. And again, the number of peaks I split into is the number of hydrogens on the neighbor plus 1. Let me do that in a little more detail here. So some splitting pattern here. A couple other features here is it's only the nearest neighbor. So let me just draw, let's say I have a CHO proton, CH2, CH2. Right. First thing you want to do is you want to identify how many environments, how many different kinds of H's do I have. Well, I have an H in an aldehyde environment. I have H's in a methyl environment. Although I do have 2 H's in sort of CH2 sort of environments, these are still 2 different environments because this one here, the nearest neighbors are 2 carbons, they're just alkane sort of functionality, whereas the red one here has the alkane functionality but an aldehyde functionality that actually might cause it to be different as well. So without looking at the actual data booklet for the numbers, I would expect TMS to show a 0. In terms of numbers, my ratio are a 1 to 2 to 2 to 3 sort of ratio. Again, I don't know exactly where these show up. I really should have looked it up there, but let's say my CHO group, if it's 1, if my CHO appeared here, it's going to be the peak of 1. I'm going to have this one CH2 because this is closer to the more electronegative group here. We would expect this one here to be shifted a little bit more downfield. Because it is a 2, I'd either expect the peak to be twice as tall, shifted a little bit more downfield, or another 2 here, sorry, color-coded here, or another peak here could be a little bit wider, okay, but not as tall. At least for the integrated trace, it would tell me that both of those are the same. Maybe this is CH2 and this is CH2. And then I have my CH3. Again, what I haven't checked here is actually where these peaks show up. Maybe my CH3 actually appears as a really narrow peak, maybe even here. I don't know. You would check your data booklet for that. The number, right, so the peak height or the area under the curve, the number tells you how many hydrogens in that environment. Integrated trace would also do that. And the other thing here is the shifting would tell me which peak. So the amount of shift tells you which group. Right. So if I did that integrated trace here to identify the 2 and the 2, it could have been a taller peak or a wider peak here. If I have an integrated trace, I just go left to right. This one goes up, let's say that much for 2. Then going across this one, it's also that much for 2. In this one here, because it's a 3, suddenly it's going to be a little bit taller. And then we go through here, that's a little bit smaller here. If they're nice to you, they would actually give you numbers 2 to 2 to 3 to 1, okay, like that. And that's how you identify your splitting pattern. Right? your Owen textbook here talks about it when you talk about doublet, quartet, things like that. They call that a multiplicity. So a multiplicity of 2 is the name of a doublet. It's just putting a number to how many peaks there are. Multiplicity of 3, a triplet. And for multiplicity, basically, you will split into the number of hydrogens on neighbor plus 1. Right. So earlier we had 1 neighboring hydrogen, so I split into a doublet. If I have 3 neighboring hydrogens, like earlier, I split into a quartet, and the relative proportions are given by Pascal's triangle. We had a quartet, 1, 3, 3, 1. We had a doublet that were even. We're all talking ratios here because if I run it for longer, all these peaks here would then steadily be taller, but at least by ratio, it's still going to be the same. So that there also gives us a lot of information. I think I called that technique 4. Remember, the power of this one here is they don't have to just give you a mass spectra question or IR spectra question. They can give you, oh, here's the IR spectra, here's the empirical formula, here's the IR radiation, NMR, and you're basically, as that investigator, trying to piece together all the information you collect. This last one here, they say you just need to know the name of it. Xray crystallography, I mentioned already, really useful in finding bond length and bond angle. Let me just do a quick overview of what's happening here. First thing, X-rays are really, really high energy, even more energetic than just exciting electrons. This one here, these ones can pass through your soft tissue, no problem. It bounces off your bones like mirrors, so that's why anytime you have broken bones, things like that, they do an X-ray to try to reflect off the bones to see the structure. What I'm going to do for Xray crystallography, this is just for curiosity's sake here, I'm going to send in monochromatic X-rays. So X-rays also occur in a range. I'm going to send in a bunch of rays that are all in phase. I'm going to send in a bunch of rays that are all lined up. All the peaks are the same, all the troughs are the same, and they're all happy. So I'm going to send it in monochromatically and in phase. What's going to happen here is as they start interacting with the layers on whatever the substance is I'm going to analyze, these X-rays here may make it varying distances. So, for example, this first X-ray here makes it down the first layer and already bounces off. The second ray here ends up going a little bit of extra distance, gets to the second layer before bouncing off. I'm going to assume for simplicity the layers are parallel and then bounces off this way. What you're going to find here is because they started out in phase, because they started out constructively interfering, there is an added amount of distance. So far, same. By the time the first ray ends up bouncing off, the second ray hasn't come through yet. So depending on the size of the atom, depending on how many more layers I cut through, I actually managed to go through that much extra length, right? That much extra length, there's no guarantee that that's going to be in phase or out of phase. That can knock me perfectly. Maybe if this distance here, if my extra distance is any n times lambda. If it's any wavelength, it could be 1, it could be 10 lambdas, deep, doesn't matter. But if it's perfectly in lambda, by the time I start paralleling the light coming off, I'm constructively interfering again, I'm going to show a bright dot. It's possible that my extra distance is exactly 1/2 of lambda. I'm exactly shifted off phase. So by the time I bounce off my specific layer, my ray here, my first ray was minding its own business, it was just doing this, but now because I traveled an extra half wavelength, when I come out of this, I might actually end up being exactly the opposite of what I want. And in that case there, waves will interfere with each other. This is perfect destructive interference. The top of the wave cancels the bottom of the wave, and I get a perfect zero wave, and I get a perfect shadow. And you're going to get the whole range between destructive and constructive interference here. So destructive here. So you get a ranging between slowly gets brighter, bright where everything's constructively interfering, and then slowly when it gets to destructive, slowly getting no wave. So that's what this is trying to show you here. We have constructive interference. This one here is perfectly destructive, but there's the whole in between as well. So we basically send in this monochromatic ray here. It interacts with the material however it's going to be. In your physics course, you actually would do this as an option to actually figure out what does it actually depend on based on the size of the radius and all that. For us, all we care is the name of the technique. But based on the shadow pattern that we get, here's a shadow pattern of anthracene here. We actually get this sort of nice contour map here. We can very easily measure from the shadowy picture left behind by the in this case here, I have my anthracene sample. It leaves behind this shadow picture. I can actually get a sense of not only what bonds, oh, it's going to be cyclic, I also can find the bond angle that way. Again, I mentioned there's a really successful case of DNA. You shine light here. DNA was known to be this sort of double helix sort of structure, spiraling in on itself. It wasn't done overnight, definitely, but basically we had, I think the fellows were Watson and Crick, basically did this X-ray crystallography. They shined the X-rays on this. They saw the diffraction pattern, and they ended up inferring that the double helix structure is for the DNA. So again, the advantage of this section here is to try to do many techniques together. With all the techniques, hopefully we can sort of triangulate on what the actual compound actually is and the detail that we're getting. All right. So if you have any questions, just feel free to let us know. Thanks.